Without any other delay, we will start the webinar. Let me just make Amo the presenter. And Amo, you can go ahead and start with the webinar.
Thank you very much, Sydney. And good afternoon, everyone. Good evening and good morning to some parts of the world. Welcome back again for this session on what's new in SolidCAM 2015. We saw some of the stuff last week on what was new. What I'm going to do this week is again run through those new things that we saw last week. In addition to that, we'll see an exciting new feature coming up in SolidCAM 2015 in a version that's already released, which is auto tilt. Basically, auto tilt is a very useful feature for mold makers if they want to cut their cores and cavities using full simultaneous 5-axis, where it takes up the 3-axis toolpath and you can provide another tool which is short of the same diameter and type, short tool, and the software automatically does the tilting for you. We'll see that a bit later. We will run through now to the new features of SolidCAM 2015, and we'll run a few things again. So what I'm going to do today is I'm going to go again and show you another part for multi-axis roughing. Okay, this is a pretty nice part. You could relate this to some frame component or something. It's about 330 by 300, about 15 millimeters in depth. So what we're going to do is we're going to rough out this whole thing, and we are going to use the multi-axis roughing for this purpose. So let me add multi-axis roughing. Now what basically multi-axis roughing will do, I'll explain to you when the calculation is on. So I'm going to use two strategies here. Last week we saw both of them, but I'm just going to refresh those two strategies. The first one being offset-based strategy, and the second one is the adaptive strategy. So we will see both of these today. Let me go with the offset strategy, and in the sub-strategy we have got offset from floor, offset from the ceiling, or morph between floor and ceiling. So we can use any of these strategies. I'm going to use the offset from floor. The floor surfaces I've already picked up, so if I can click on show, and these are the picked up surfaces for the floor. These are the surfaces to which the toolpath will be normal. And in wall surfaces, I already have picked up the entire model as my wall surface. Now the software is pretty intelligent. What it basically will do is it will isolate the wall surface from the floor surface, because it knows which are the floor surfaces, and it will work only in the pockets or in the regions where it needs to cut. So it understands, or it differentiates between the wall and the floor surface. All right, we'll keep an offset of 0.5 millimeters for both of these. I'm going to use a 12 corner radius to bull nose. So this is a bull nose tool that I'm using, and this is how my tool would look like. Okay, let's select this tool. Levels will provide an entry distance of 5 millimeter and exit safety distance of 2 millimeters, and my retract plane is 20 millimeters from the last point of entry, or the first point of entry and the last point of exit. Why I don't see the clearance plane? Simply for the fact that roughing, SolidCAM's multi-axis roughing basically works on the principle that the tool is always going to be normal to the floor surface. So when it retracts, it's actually going to retract normal from the floor surface. So That's the reason why we don't have a clearance type and clearance plane out here. It's only basically being done from the retract plane, so we'll provide a retract of about 50 millimeters. Constraint boundaries, I'm going to pick automatically. Toolpath parameters is where I'm going to spend some time because this is going to make or break my toolpath. The first is a cut tolerance. Since we have used an offset of 0.5 millimeter, I generally use a cut tolerance, if it's a big part, 0.1, 1/5 of the offset. Step down, in this case, I'm going to give a step down of, let's say, 8 millimeters, just to show you how the toolpath looks like. We also have a possibility of providing a constant step down or a number of slices. That means I can say to the software, instead of giving me step down of 8, give me just 2 depth of cuts in the entire geometry, so it will equally distribute the depth in 2 depths. Okay, let's use the 2 depths. The maximum step over in this case, I'm going to go half of the flat area, which is 12 minus 48. 8 by 2 is 4 millimeters. So I'm going to go 4 millimeters for my maximum step over. Sorting, I'm going to use climb, and the machining is going to be by regions because there are several regions out here. So you can see that the tool will go into every region, it will finish it, and only then go to the next region. All right. Smoothing, yes, we would like to smoothen the corners, we would like to smoothen the final contour, and we would also like to smoothen the links. Let's go to the link. The approach and the plunging into the material is controlled by my ramping. So I can use different types of ramping. I can provide auto ramping, that means the system will decide what's best needed for that particular area and then put the ramping. Or I could specify a line, or it could be helical, a zigzag, or a profile. I can specify what kind of ramping I want into that. Generally, we prefer to keep auto to let the software decide what it wants to do. But in some cases, customers or the users would like to control what kind of ramping goes into the area, so you will use that kind of ramping. Ramp angle of 5, and the ramp length is generally about 80 millimeters, or 80% rather. In the approach, I want the first approach to use ramp because it's entering a solid block. When it's leaving, there's absolutely no ramp needed because it just needs to retract out. In the links, I'm going to use ramp. Between groups, I'm going to use ramp. When it goes between slices, I would like to use a ramp. When it links between regions, I would like to use ramp. So I'm using ramp in almost everything. Okay, that's all that I need to do. I'm just going to save this. Okay, and calculate. Right, this would take about a minute to calculate because it's a big part. While it's calculating, let me explain you the philosophy of multi-axis roughing. Basically, multi-axis roughing is meant for parts like what you're seeing on the screen right now, or it could be even a twisted part, which I will show you a bit later once this part is done. Multi-axis roughing would generally be used in those parts where users believe that to rough out that particular part, they would probably need more than one setup. In this part itself, you can look that it cannot be done in one setup because there are undercuts on walls, there are certain areas that go into the shadow region, so it cannot be done in one go. In such cases, multi-axis roughing comes handy because what it will do is it will basically align the tool normal to the floor and machine all the walls that are there on the part. Alright, so it has completed the calculation and we can look now at the results. So let me highlight the toolpath. Okay, that's how the toolpath looks like. You can see that whenever it's entering into the material, it is entering via ramping, and whenever there's an exit, it just exits. It doesn't need any kind of ramps. So it's a pretty neat way in which the roughing has been performed. We can have a look of this roughing on our machine simulation and how it looks like. I have defined a DMU 100 monoblock machine which has got the movements on head as well as on the table. On the table we have a rotary which is along X, and the head is normal to Y. So the typical DMG machine. Okay, let's run the simulation. It's pretty fast. You would be seeing in blocks, but it's pretty smooth out here. Right, let's pause the simulation and let's check if we can perform the simulation in Solid Verify. Okay, that's the stock. So let's run it slowly. Okay. So what this basically has done is, with just a click of a button, it has generated a 5-axis roughing toolpath. So if I generate a G code out of this, okay, you can see that we have a full 5-axis toolpath out here. Okay, it's because it's generated a second file. All right. What I'm going to do now is I'm going to copy this example and toolpath and paste it, and we will change the type of machining or the strategy to adaptive to show you also the adaptive strategy, which basically is similar to what we have inside SolidCAM eye machining, where it tries to take constant load, but only thing in this is it will vary its side step, and the toolpath looks pretty similar to what we have in eye machining. So let's select the same tool, and the only change that we're going to make now is out here. The maximum step over is 4, and then there's a desired step over. Because it needs to vary its step over, there are 2, maximum and the desired. And because we are going to do both climb and conventional, I can define when it is doing climb, what is the percentage of step over it needs to take, and when it's doing conventional, what is the percentage of step over it needs to take. This is essential because in some users don't like that it takes a big step over when it's doing conventional milling. So they would like to restrict the step over. In this case, I could put that step over as 50% of the original step over, whereas when it's doing climb, it will take 100%. Okay, just for the sake of today's demo, I'll put it both at 100%. And instead of 2 slices, I'm going to put 1 slice because I would like to show you how the toolpath looks like. Sorting by regions again. Smoothing is not needed because the toolpath itself is pretty smooth, so you don't have the smoothing options coming out because it's using the spiraling technique. Link, we are going to use everything the same. However, we do have a thing that we need to change out here, and then we can switch to adaptive. Okay, great. Right, so we've done our setting. Let's save this, and I'm going to run the calculation. So what this basically would do is it would generate a toolpath that would go into the material in one full step, use the full cutting length of the tool, and it will try and create as many spiral toolpaths as possible depending on how the geometry is in this particular part. So it could create 6, 7, or even 10 different localized toolpaths for this particular part, depending on how the whole thing looks like. Okay, so what it is basically going to do is it's going to provide me with a step over between 4 millimeters and 3.2, and it will adapt itself between those two step overs to create a toolpath which will spiral around. Let's say if it's doing the geometry here, then it will spiral around inside this rectangle. If it is doing around here, it will spiral inside the circle. But if it's outside here, it will take the outer contour and the inner islands into consideration before creating a spiral. And the same thing goes to island over here and also to the pocket out here. So it will create a pretty interesting toolpath which will mimic iMachining but in 5-axis. It would take another 35-40 seconds before the toolpath is completed, and after that we will go ahead with our other new features, because I would like to spend some amount of time in showing you auto tilt, because I've got some nice parts today to show you auto tilt and how it works with the new function inside SolidCAM. Okay, the calculation is almost done. It's doing the toolpath preview, and this is how a toolpath would look like I exactly said. Now, it's unable to get into this because of the size of the particular geometry, but it's moving into several other areas. You can see that whenever there is an entry, it's taking a ramp, it's nicely ramping down and then creating spirals. However, in some cases, for example, when it's doing the channeling, it's doing machining on both sides. Okay, so you can see that it's generated pretty interesting toolpath. Now, if I run this again into machine simulation, it would be pretty interesting to know how the machine looks like. Okay, let's go into the area here and let's look at the simulation. It's a complete simulation in which you will have all the axes moving together. On your screens, you'd probably see a cluster of movements together, so you not probably realize if it's smooth. Anyway, we'll have this movie up on our website so you can see this exactly how it would move on the machine. Right. So the conclusion of multi-axis roughing is that whenever you have parts or pockets where you would like to rough them out in one go without change in setup, and which need more than one setup to do, especially if the walls have undercuts and stuff like that, you can easily use multi-axis roughing. You can also use multi-axis roughing for the purpose of finishing the floor, because it gives you one single homogeneous toolpath. So a lot of uses for multi-axis roughing, but the most important one is to rough out material from pockets in full 5-axis. Right. Let's go and see some other new features that we introduced inside SolidCAM 2015. And the other one that we are going to talk today about is the feed control, a very interesting feature. And this actually works with both 3 as well as 5-axis. Now, what I've done is, last week I showed the toolpath in 3-axis. What we are going to do is today generate the toolpath not in 3-axis but in simultaneous 5-axis using Swarf. So I'm going to add. Okay, let me change the machine. Okay, continue. Yeah, and let's measure the height so that I can put that in the setup. It's about 120, so I'll create a height of 120 so that it moves up by 120 millimeters for my machine simulation. And let's add Swarf and geometry. The Swarf surfaces are basically these surfaces. Okay, I can show you in fact another nice feature inside this part as we speak. Okay, let me pick all the surfaces. Okay, that's the last one. Just to see what has been picked up, let's click on edit. Can show them later. Okay, so that's faces. Right, we are going to use automatic, and in the tool we will use not 16 millimeters. In fact, I'm going to use a 12 millimeter ball nose. Okay, let's select the holder. Okay, tool axis control. I'm going to minimize the rotation axis. It's not needed, in fact. Right, so let's quickly generate the toolpath. The toolpath is calculated. SWRF is getting better and better with every release of SolidCAM. It's much faster now to calculate SWRF operation. Okay, you can see what has happened now here. The tool has entered into the floor. That's because we did not tell to SWRF what was a floor dimension. Also, the holder. So let's take slightly longer one. Let's measure what is the height. Okay, that's about 75. Okay, let's take 100. Okay, let's pick this. Let's go to geometry and select the floor surfaces so that it doesn't collide. Calculate again. Calculation is done. Let's run the simulation. Okay. Now, what I've done basically is I've not provided any feed. Okay, so we will also see that. Okay, you can see that the feed is constant. Even if it goes into the corners, it's pretty much constant. There's no change to the feed rate, and it's going pretty much the same, constant everywhere. Now, what happens when you're using a lengthier tool is that you do not want to go into the same area or into the corners with the same feed rate. Okay, so you would like to drop your feed rate by, let's say, 30%. So what we have in SolidCAM is a new option under the tool called as a feed control. And sorry, this is not for SWRF, but for SWRF, yes, we definitely like to have the feed rate adjusted on the edges. So we can go with a minimum feed rate of 10% and a maximum of 100%. So let's change that to, let's say, 50% and 100%. And we can adjust the feed rates on edges for fanning and also for cutting depth. So we can have, for example, we can have 100% for the first 50% of the job, and then we can drop it down to 50%. So we can readjust and change the whole toolpath as per the new feed rates, and this is also a new feature inside SolidCAM. You can see the feed rate now dropped not to 100 but to 93.24, and it's again dropping down. It's going up. It's changing itself to 91. You can see that the feed is not remaining constant. It's adjusting itself with the geometry that we asked it to check itself with. So it's not a constant, especially when it goes over the fanning area. You can see that it was 100% because it was a straight area out for it. Okay, you can see that it's not constant feed rate that it's going with. Right, now this is one feature of swarfing. The other one basically allows us to use volumes of material to drop down the feed rate. How do we do that? For example, if I've created a 3-axis toolpath with the tool, and in the data I've defined a cutting feed rate of 2000 millimeters per minute, and I have not provided any feed control. Okay, so let's calculate the toolpath. Okay, now if I take the tool and if I move it, it's constant. There's no change. You can see that it's constant, moving around 2000 millimeter per minute. There's no change to the feed rate. So what we're going to do now is we are going to use feed control zone. How does feed control zone work? It works in two ways. First, I can select the geometry of the part to be machined itself. For example, I'm selecting this fillets, inside fillets, selecting all 8 of them. Okay, and I can say whenever it is within this particular face, that means starting from this edge going up to this edge, whenever it is in this zone, the feed rate must be dropped by 50%, and whenever it is outside that zone, it should be 110% and not 100%. Okay, let's calculate it. Let's run the simulation and see on our feed out here how it looks like. Okay, so you can see that instead of 2000, it became 2200. That's 110%. Let's go ahead. As it goes into the corner, as it comes into the corner, it comes into the zone, it drops it to 1000. That's 50%. And it will continue moving into the zone at 1000 and then move ahead by 2200. It hits the second zone, drops to 1000. It goes in 1000. Then to 2200 straight away. You can see that all the straight areas which I did not pick up as the zones are now at 110%. The second method, which is another interesting method, is we can provide not the surfaces or not the areas of the cutting surfaces or the drive surfaces, but to use volumes of material and place them into regions where we want the feed rates to be dropped. For example, I have got these 4 green volumes out here, and I have placed them at corners, but it's not starting exactly from the top, but it's starting somewhere from midway. That means I can now control my feed rate not based on this complete surface, but only into certain areas, and that too at certain depth. So let's pick new surface, and I'll pick the color from the model and I'll ask it to find. So it's found 4 volumes. Okay, and the same principle, of course. Let's save and calculate. Okay, the calculation is done. Let's run the simulation. You can see that there's no change to the feed rate. It's just 2200 because it's out of the territory. Even though it's going into the corner, it's still going at 2200. This could be done basically where we would like to use a shorter tool. Okay, the moment it's down, the tool is entering the volume, you can see that from 2200, the moment it gets into this volume, the feed rate is dropped to 1000. A very nice feature where you can control feed rates at different portions on your job exactly the way you want and exactly in the area where you want. So you can be very specific on the area, and you can be very specific with how much feed rate you want to achieve in this area. Right, so this was about feed rate control. I will now move to the most important release, or the most important feature of this release, which is auto tilt, and this is what we're going to show today. Right, so let me open a simple part first to explain how this whole thing works. Okay, I've got a nice core in front of me, core of a die, of a plastic mold, and I would like to machine this in constant Z. So what I've done is I've created a constant Z toolpath here with depth of cut of 0.5 millimeter, and I'm using a 10 ball nose tool, a lengthier tool, just to generate the entire toolpath. We're not much bothered about the length of the tool right now. So I'm going to calculate the toolpath. Should calculate pretty quickly. And then what I'm going to do is I'm going to apply the new feature. Okay, the toolpath is calculated, and it says that the minimum tool length that is needed to cut this part without the holder colliding in with the part is 66 millimeters. Fair enough. So let's see how the toolpath looks like. That's how the toolpath looks, and I would now like to cut this part not with a tool with 66 millimeters, but with a tool much shorter than that. I would like to use a tool with only 35 millimeters out of holder. Why am I trying to use a shorter tool? Because I know that the moment I use a shorter tool, it's more rigid. My surface quality is much better. But because it's a short tool, I must take into account the holder geometry, and that should not collide against my part geometry. And this is where the auto tilt comes into picture. This is a short tool, really very short, that we are using today for this purpose. Okay. So I'll add new milling operation, convert HSM to Sim5x. So I'm converting an existing HSM toolpath to Sim5x. Okay, what did you have earlier in the conversion? We had the conversion itself, where we would provide the source operation, we would provide what cut tolerance and arc approximation tolerance that would be needed, and the software would ask us what would be the conversion link type. Do you like to relink, or you would like to use the links from HSM itself? The feed rates, whether you would like to use the same feed rates or you would like the software to recalibrate the feed rates. Okay, and then in the tool axis control, we had to provide what kind of a tool axis we needed for this 5-axis toolpath, and we also had the gout check, where we used to enable tilting of the tool 3-axis to 5-axis conversion. So there were a lot of things involved into it, and you did not know what was the right solution, what should have been used, what should not be used. All those things are of past, because we have introduced a new function inside convert, and that's auto tilt. Okay, auto tilt works exactly similar to the other automatic toolpath calculators like multi-blade, like port, or even for that matter Multiaxis Roughing. What it basically will ask me is the source operation. Now, because there's only one source operation, I don't have any other means of selecting another operation, because there's no other operation inside. The only thing now it asks you for is the cut tolerance and the arc approximation tolerance. By default, it goes to 10 microns, because that's what has been done, or that's what has been used to calculate the previous HSM toolpath. The tool we're going to use is a short one. Okay, this is the tool that we're going to use. We're not going to use the original tool, which is 68 millimeters, but 35 millimeters. Okay, remember that we need at least 66 millimeter for it to do the cutting without the holder colliding with the part geometry. So I'm going to select this toolpath, or rather this tool. Levels, you can see everything is grayed out. That means there's nothing applicable, because it's all going to use everything as it is from the HSM toolpath. Tool axis control, some new things, but there's nothing to worry about because it's only asking things that probably might matter to it when it's calculating. What it basically asks is, if the tool does not fit into a certain area, especially the corners, what should it do? The default option is keep it at 5-axis, but stay close to vertical. That means stay close to 3-axis. The other option is you could say keep it at 5-axis, but stay close to, let's say, 5 degrees. Don't do much. Okay? But the default works fine, where we ask it to generate a 5-axis movement, but stay close as possible to the 3-axis movement. When the tool does fit, that means it can go into that region. Short distance, or the distance is small, we are asking the software to go back to 3-axis. That means it will tilt itself back to 3-axis. And where the tool does fit, long distance, it will go back again to 3-axis. So we have got this tool axis control, which is different from what you have seen in the conversion, but most of the defaults work fine. They work just fine with your any kind of part that we're going to see today. We're going to see 3 different parts. All right, in the links, again, everything is grayed out because it's going to use all the links from HSM. Clearance data, we would like to keep a clearance of 2 millimeters from the holder, from the geometry. So that's what is being defined out here. The interesting part is that you don't see any gauge check options here. Why? Because gauge check is hard-coded inside the system itself. It's built into the system. That's how it becomes automation or automated. So we only have to define what is the clearance that we need from the holder to the part, from the arbor to the part. Once this is defined, you don't need to define anything else. There is obviously an option to define additional clearance, workpiece clearance. For example, you would like to provide an additional workpiece clearance. That also is possible, but it's not necessary because we already have provided quite a sufficient clearance out here for our holder. All right, so what I'm going to do basically is I'm going to save this operation. The moment I save this operation, you can see that my HSM toolpath, like any other conversion toolpath, it's suppressed. Only the convert is switched on, and we will calculate this. It's loading. It will load the original toolpath, run its gauge check functionality, and then create the tilted toolpath. It would take about 35-40 seconds. I believe it's a pretty good time for it to calculate. It's almost done. It's running the final gauge checks. We believe that this particular function that you have in front of you, the auto tilt function, is going to be very useful for the mold makers, because let's assume that they would like to cut a core or a cavity with a short tool, and they do have a 5-axis machine, and then it's very useful because they can go really deep without having to use longer tools. And that would provide them with, number one, it would provide them with a rigid cutting that would not only improve the surface quality, but it will also improve the time needed to cut the part. It will bring down the time from the existing few hours to maybe 50% of it, because it's using a short tool which is pretty rigid. All right, so the tool path has been recalibrated. You can see that none of the links were touched. It's the same link, okay? It's the same HSM link. It's the same HSM connection that it is using. Nothing was done. The only thing was done was it recalibrated itself to provide a 5-axis tilt whenever the holder is coming in close contact with the part. So let's run the simulation. I'm going to switch off the toolpath, and let's run the simulation from top. At least for the first 35 millimeters, we know very well that it's not going to do any tilting because it can still do the cutting in 3 axis. Okay, so the moment it goes below that value, we can see what is happening. Okay, it starts tilting. It starts tilting to avoid the holder from colliding with the geometry. You can see that it's kept that clearance and it's moving away. And as it goes down, this clearance value will, or the tilt value will only increase. You can see that when it's at this point, when it's at Z minus 43, you have got a different clearance altogether here. It's tilted itself to avoid the holder from colliding into the part. And this did not take more than 40 seconds for it to calculate. So let's run the machine simulation and see how this whole thing looks like in the machine simulation. The best part of auto tilt is it's really automatic. You don't need to specify anything to it. Let's go to the machine and let's go to the front view. Okay, that's our machine. I'm going to run it for some portion pretty quickly, or maybe I can drag the motion here. And as it goes on the side, I would like you to look at it. You can see that the head starts tilting. The head starts tilting and it starts rotating on the side. Now what it is doing here is it's kept the head stationary and only the C-axis along with the X and Y are moving in order for it to compensate and create that movement. So it's pretty nice motions where your B-axis is tilted. It's tilted almost at minus 15 degrees. You can see on the side when I move the slider. Okay, let's pause it for a moment so you can see the updated image. And as I move it down, you can see that my tilt is increasing. For example, I moved down Z to almost to the bottom, and my B-axis is now at minus 23. So as it moves down, the angle starts changing. So this is one of the key highlighting features of auto tilt, is that it doesn't keep the angle constant. In our conversion method, there was a possibility to keep the angle constant. We could find out the maximum tilt needed and keep that tilt constant right from top to bottom. In this case, it is not needed. It keeps changing the angle depending on how close the holder is coming to the particular geometry. Right, so very important and very useful feature for mold makers. They can now cut core and cavity, even if it's a big length and if they have a 5-axis machine, they could use shorter tools and run parts on 5-axis by just converting their existing 3-axis tool path to 5-axis. Okay. Another part I would like to show you in auto tilt. Now that particular part is a bit complex, so I have already done the calculation myself. Okay, it's a die casting die. That's the part, that's the cavity of die casting die. And what I have here was, I had this 3-axis toolpath, a Z-level machining. The tool that I used was T1, so that's 10 millimeter ball nose with an outside holder value of 50. Of course, I did not generate the toolpath, but the toolpath went all the way down up to minus 75. And the same toolpath was then cut or then converted to 5-axis using another tool of the same diameter but an outside holder of only 45 millimeters. That means I've taken a much shorter tool to go much more deeper into this cavity. This is much more complex than the earlier one. In the earlier one, the external part was all open, so it could tilt and move around. In this case, it is slightly tricky for it to do auto tilt. Even in this case, SolidCAM manages to perform the auto tilt operation much nicely, keeping the same linking what was there earlier for the HSM operations. Let's run the simulation now. Okay, for some portions we are going to run it very fast, and as it goes down, I'm going to stop and show you the tilt. For the first, I think for first 45 millimeters, you would not see any kind of tilting. It's only after that that you will see the tilt. Yeah, started tilting now, and the tilt also is very smart. It will only tilt if it's needed to. That means in case there is no collision between the holder and the part geometry, or the part geometry is quite away from the holder, it will not tilt to 5-axis, but it will be 3-axis itself. You can see that as it goes into that region out there, where I'm marking right now, moving my cursor, that area out there is where you're going to have the proper tilt. Okay, let's go ahead. And you can see that here it tilted because it's going to come pretty close to this edge. The holder would come pretty close to the edge of the part, so it's tilted itself to avoid the gouge. Now, how would this look on the machine? Again, it would look pretty interesting. As you can see that we generated a constant Z toolpath. The first one was not from the top, but it went somewhere in between and then came up and started from the top. Now, you can also see how this would affect to a 5-axis toolpath, how this would work on a 5-axis machine. Okay, that's done, and it's now moving into the machine. Open the door, and let's go into the area so that I can show you how it moves. So the first one, the first machining doesn't have, but the moment it reaches, it's actually machining this region out here inside. It's actually cutting inside the part. It did not start from the top, but it just went inside. And when it's trying to do this, it's going to do the machining in full 5-axis. So let's go to the front and slightly rotate it. Okay. You can see that it's already trying to rotate and machine it in 5-axis. Very interesting. A 3-axis toolpath immediately converted to 5-axis. Okay, let's go down here and see somewhere here. Okay, let's run slowly. So you can see that it's tilting both the axis C and B. So what it basically did was to take up the complex HSM toolpath, just apply new tilts, do the gouge check, everything automatic within the system. We did not have to intervene into the system. It's one of those few systems that does most of the things automatic on by itself without having to specify anything. What I've also done for this part is I've generated the rest machining toolpath, and I converted the rest machining toolpath to simultaneous 5-axis. Okay, so I've taken this toolpath, converted it to Sim5x. Let me run again the simulation, and let's run this in HostCAD, not to go to the machine. Okay. As it comes to the wall, you can see that it's tilted itself. Okay, it's tilted itself because it's now trying to avoid the gouge between the holder and the geometry. So it's tilted itself very nicely to avoid that collision between the holder and the part, and still do rest machining. Very, very important feature, especially when you're doing large dies and you would like to move into the area using shorter tools and keep the toolpath gouge free. So it's very nice feature, and most important, it's completely automated. That means it doesn't need much of user's intervention. All they need is to provide the old toolpath, and it converts to 5-axis. I'll show you another part before we end the webinar. So let me open up another part. Again, this is a die casting die. What I've done basically is I've taken a 3-axis constant set, or helical toolpath in this case, and I've converted into a fully automated, fully gouge checked, collision free 5-axis toolpath. Right, so let's look at again the simulation. Let's run quickly. As it goes down, we can start looking at the effects of this toolpath or the conversion. Okay, so what you have here is it's machining, those rib areas, okay, and as it goes down, it's going to be very interesting. Okay, so that's not anywhere close to the values that I defined, so it's keeping it in 3-axis. And as it moves forward, you can see that it starts tilting very nicely. As it's moving forward, it knows that it's coming close to this geometry, and it's coming within the area or within the distance that I specified. And to avoid that, it starts nicely tilting itself away from that particular region, so that there is no collision between the holder and the part. Okay, so it's done that pretty nicely. You can see that at any given point of time, it's trying to maintain that gap, that distance that I specified as a clearance distance between the holder and the part geometry. So a very, very useful feature that we have released in 2015, the auto tilt, converts your 3-axis HSM toolpath to a collision-free 5-axis toolpath at a click of a button. Nothing more, no more inputs needed. It only needs the old toolpath and the new tool that you're trying to use, and it just converts your 3-axis toolpath to 5-axis toolpath pretty quickly. The calculation also is pretty quick. For example, for the part of this size and this toolpath, it took about 2 to 3 minutes to convert it from 3-axis to 5-axis. Right. So we come to the end of our What's New series on 5-axis for SolidCAM. We would be continuing next week on some other topic. And if there are questions, I would be more open for questions. If you have, okay, please ask the questions.
Well, thank you very much. It's actually very, very interesting. We have actually those two quick questions. The first question was, I believe this also came in when you were showing the multi-axis roughing is that is a floor surface necessary for multi-axis roughing?
Yes, it is absolutely necessary because the whole algorithm or the whole software works on the principle that the tool is always normal to the floor surface. So you have to define the floor surfaces.
Okay, and the second question was, this has to do with the feed rates. Did you create the volumes for feed rate control in SolidWorks? If so, are they in a new part inside the CAM assembly?
Let me open up that part so I can show you quickly what I did. It was in fact generated inside SolidWorks itself and taken into SolidCAM. So if you look at my tree, it's actually not part of anything. I've just created it inside the design model, and if you look at the solid bodies, these are the 4 solid bodies that I used to control my feed rate in the corners. They can be part of your design model, or they could be completely different part that is there in the assembly. But it has to be there in the file and at the right place.
Okay, Ahmad, thank you very, very much. I found this very enlightening. And for everyone in the webinar itself, this webinar has been recorded as usual and will be available together with the parts used later on. And again, thank you very much for joining the webinar, and see you again in our next webinar. Take care, Ahmad, and have a great weekend, everyone.
Thank you. Thank you. Bye.